let's get started. So the first thing that we're going to look at is differentiation. So it's about looking for the gradient of tangents, as we spoke about before. So here we've got a graph. It's about the temperature of a bottle of water taken out of a fridge and the temperature as it's been left in the sun. And so here's your explanation of what's happening. So there's a couple of things that we can look at when we're looking at this diagram. So one thing that we can talk about is the average increase. So if we wanted to look at how much it's increased from the beginning up to 20 minutes, what we can do is we can draw a triangle, and then what we need to do is work out the gradient of that triangle. So if we're looking at these values, then we can see that the horizontal is 20 minutes, and your vertical is also 20. So what that means is the average rise in temperature is 1 degree per minute, okay, and that's 20 divided by 20. But you can see that from the actual graph, so you're looking at the black bit, initially it's increasing faster, but then as time goes, it increases slower and slower. Okay, so it doesn't make sense to say 1 degree per minute, because definitely if we look at that first degree here, that increase isn't 1 minute. It's actually a little bit more than that. But as time goes, in each minute, the temperature is increasing by a slightly smaller value. So the average is just taking the gradient between those 2 points and calculating that. What we often want to work out is actually the instantaneous rate of increase. Okay, so at that point in time, how fast is the temperature increasing? Okay, and in order to work out that, we need to look at a tangent. Now, back when you were looking at circles, we talked about tangents there. So if I have a circle, a tangent is a line that touches that circle in exactly one point. We can also draw tangents for any other types of graph, say for example this graph. So a tangent is a line that just touches the curve. So we can look at A here, okay, and this line that's already been drawn for us here. You can see that this line just touches the curve at A. And so we can work out how fast the temperature is increasing at that particular time by working out that particular gradient. So that's what we're going to do in example 1. So I've given you the answers already here. So we're going to work out each of the gradients, and then we're going to fill in that table. So when we're looking for the gradient of the tangents, what we're going to do is we've had some tangents drawn in already. We've got a tangent at O, A, B, and C. So what we're going to do is we're going to look at this right angled triangle and work out that gradient. So the horizontal is 10 minutes and the vertical is approximately 1.4 or thereabouts. So when we go to work out the gradient is rise over run, okay? So it's 14 degrees. So 14 divided by 10, which gives us 1.4. So at the origin, the rate of increase is 1.4 degrees per minute. What we can then do is look at A. So when we're looking at the gradient for the tangent at A, what we're doing is we're taking this right angled triangle and we're working out the gradient here. So the horizontal is going to be 20, and we need to look at how much that vertical is increased by. So how I've worked it out over here, I've estimated it's about 27 and 13, so it's 27 minus 13, that's how much the increase is, over 20. And so at the 20-minute mark, the temperature is increasing by 0.7 degrees per minute. We've done the same with B. So again, there's your vertical, There's your horizontal, and you're going to work out the gradient there. And I've estimated to be 33.5 degrees minus 26.5, so that's about 7/20, or that's about 0.35 degrees per minute. And if we do the same at C, we ended up with 0.175. So you can see as time progresses, the temperature, the rate of increase in temperature is actually slowing down. Okay, and we would expect that if we were to put some water out in the open. Initially, it will start increasing in temperature faster, and then over time, it will be slower. What we can also do is we can then take these values and draw another graph with these particular values. Okay, so we can draw a number plane, we can put x along the horizontal, f dash x along the vertical, and we can also look at what this graph is going to look like. Now, when we did these calculations, often when you're looking at the diagram, you're not going to be able to get perfect values, okay? And also, like when you draw your tangent in, if your tangent's slightly off, you'll get a different value compared to someone else's who's drawn a tangent. So this isn't an accurate way of working out gradients. Calculus actually gives us the accurate method. But before we get to that, let's have a look at a couple of easy graphs and easy equations that we can work out gradients for, even with just the knowledge of mathematics that we have at this point in time. So a geometric definition of a derivative is basically it's the gradient. Okay, so the gradient of the tangent of y equals fx at each point on the curve. So if we're looking at linear and constant functions, we know that for these graphs, the gradient is always the same at every single value. If we're looking at the gradient of a straight line, we get a certain number. So whatever the gradient is of any point on the line, that's going to be the gradient of the whole thing. So if we have a line y equals mx plus c, but I've just used fx just so that's function, the gradient is going to be the gradient of this line, and we know the gradient of the line is m. So if I have a straight line and I know the equation, then the derivative, okay, is going to be that number, because your derivative means you're looking for the gradient. So it doesn't matter where you are on that line, the gradient is always going to be the same. If I'm looking at a horizontal line, we know a horizontal line, y equals c, it has a gradient of 0, which means your derivative is going to equal to 0. So these are things that we can now say that we already know of. Okay, so we know about gradient, but now we can link this idea of gradient to the derivative. Here's a couple more examples. So we had two diagrams. In these ones, we've got equations. So write the derivative of each linear function, so linear, straight line. So what you're really looking for is what's the gradient. If we look at fx equals 3x plus 2, the gradient is 3, so that means your derivative is 3. If we look at this second equation, we've got 1 minus 3x over 4, so we're going to split that into the two fractions. Okay, so the 1 and the minus 3x, and the gradient is going to be the value on the x, so that's negative 3 over 4. For our last equation, fx equals negative 1, that's a horizontal line, okay, there's no x's over here, so then the gradient is 0, so your derivative is going to equal to 0. Another type of thing that we look at are semicircles. So when we're looking at a semicircle, this gets a little bit tricky, but this is a really important rule that we're going to be using in order to work out a gradient on a circle. So the radius of a circle and the tangent at the point are perpendicular to each other. Okay, so what this means is there's your radius and there's a tangent. There's a theorem that states that this is always going to be perpendicular. So the radius and the tangent are always going to be perpendicular. So what we can actually do here is we know the equation of a circle, semicircle, square root of r squared minus x squared. So if we can find the gradient of the radius, then we can use the ideas about perpendicular lines to work out the gradient of the tangent. So we know gradient of the radius, rise over run, there's your triangle. Rise is y, run is x, so it's y over x. Now, if I have a value of x, we can see y is equal to the square root of r squared minus x squared. So I can write that the gradient of the radius is the square root of r squared over x squared over x. In order to work out the gradient of the tangent, remember we know m1 times m2 equals -1 for perpendicular lines, or we can also write that as m2 equals -1 over m1. So if I've got the gradient of the tangent, that's going to be -1 over the gradient of the radius. So if we go and simplify that, we end up with the gradient of the tangent as -x over the square root of r squared minus x squared. So if we wanted to do a little bit more with this, what we can do is you could be asked to find an equation for the gradient of the tangent. So basically we're looking for the derivative. So if I have a diagram as shown here, we know that if I've got the semicircle, the square root of 49 minus x squared, 49 is the square of the radius, so we know that the radius is 7. So this point on the graph, on the circle, is going to be x, and the y-coordinate will be the square root of 49 minus x squared. We can find the gradient of the radius, okay, rise over run, and using that we can then work out the gradient of the tangent. And once we've got the gradient of the tangent, we know that f dashed x, okay, so the derivative is -x over the square root of 49 minus x squared. Okay, so we can now write out that equation. Some of the terminology that we use a fair bit of, these are words that we will use quite a lot of, and you'll be asked to find these equations, or you'll be asked to solve things with this terminology. And I've got a diagram just down here. So the first one, let's start with the third dot point. We just talked about a tangent. So a tangent. So when we're looking at a circle, we said it was like it just touched it, and it was the only point that it touches. When we start looking at curves, in actual fact, a tangent could cross through the graph at another point, as you can see down here. So we can see the tangent is here, but it does also cross over the graph again, and that's perfectly fine. But the point of a tangent is that we're looking for the gradient at a particular point where it just touches the curve. Okay. Another word that we see a bit of, chord. So we did use that in circles as well. So a chord is just 2 points on a circle and we join them with a straight line. So we can do that with a curve again. So we've got 2 points and we're joining them together, and that's a chord. A secant is a line that passes through the 2 points, okay, and that's another thing that you would have looked at with circles. So if I draw a line straight through the middle of the curve, there's my 2 points, and it doesn't stop. So you'll notice with a chord, it has a start and a finish point. A secant doesn't actually have a start or a finish point, okay, so it's just one long line. And the last one is a normal. Okay, so a normal, I haven't drawn it in the diagram because it's going to mess up my diagram. But a normal is a line that is perpendicular to the tangent at the point. So I'll just draw it in here. So a normal would be a line that's going out this way. I'll just move it down here. And it's perpendicular to the tangent. Okay, so that's your normal. So that's another line that we do use a fair bit of. Okay, I'd like you to go have a go at a couple of questions. So it's exercise 8A. Now, with these questions, some of them you'll be asked to draw, like use a diagram, and I've given them on the next page here. Okay, so that's the diagram for question 1, and this one's the diagram for question 3. Okay, so if you print these off, then you can actually draw on these, annotate on them in order to solve those particular problems. With question 2, it asks you to use graphing software or try to be accurate and things. If you have a look in the Google Classroom, I've actually shared with you a link to a GeoGebra thing that I've just put together. So for the time being, if you could just take H and just make that 0, we're not really worried about that at the moment, and turn the tangent on. So what that tangent does is it draws a tangent in, and it also provides you with the gradient of that tangent. Okay, so what you can do is you can go in, you can change the value of the x, and then you can see that it will produce a new gradient for you at that particular point. So you may need to shift it up and down, left and right a bit, but you should be able to work out some accurate tangents using that. We will be using the H part in our next lesson. So not today, but in our next lesson we'll use the H, and I'll show you a couple of other things we can use with that.